Okay, this is the do now for today, and the do now was to get 3 kinds of substances that ionize in water. What are the kinds? And then to give one example of each. Before I set you loose on this, I showed you these 3 examples, and now we're going to go on from here. And I'm going to need a pointer, so let's get that here. Up and pictures. Let's make it in red. Okay, and we're good to go. And we're good for a pointer. Okay, Aline, just a sec. Aline, would you please tell us what do you have for the category for sodium chloride?
I put lithium oxide.
Well, lithium oxide is another good example. LiO, okay, that's a metal with a nonmetal. And that works just fine. The Li, you'd have 2 of them because oxygen is a 2-, right? Okay, what category does this fall into? A metal with a nonmetal. What do we call those? Nope. We did this before we ever started. Nope, not a metalloid. Who can help her? Destiny. Salt. Very good, Destiny. All right. That is a salt. Okay? A salt is a metal plus a nonmetal. Okay, so you gave me 1 example there. You could give me, why don't you give me 2 more? Real simple. Any metal with any nonmetal. Magnesium oxide, that works. That is an ionic compound. Yes, very good. Yeah, these guys form ions. They all form ions. Okay? All of these. And let's do this. All of these form ions. Ions. Okay, so what's another one? Stick with column 1 or 2 and then do any nonmetal with that. Calcium fluoride, CaF2, that would work. So there's all kinds of examples of these. Good job, Aline. And Andrea, you're up next. Hey, Andrea, for HCl, what kind of a compound is this? It is an acid, yes. And so this guy is an acid, and an acid will have a hydrogen at the beginning. Okay, always. And what other acids did you come up with? Nitric acid, yes, that one is HNO3. Okay, and what can you give me a couple more? Hydrofluoric acid and acetic acid. Yeah, there you got 6 of them. So you got nitric, acetic, hydrochloric. You got sulfuric, hydroiodic. Okay, HI. Yes, just like hydrochloric. Yes, hydroiodic. That's how you'd say that. So yeah, we're good here. All right, next up is Louisa. Okay, Louisa, what do you have for the NaOH? What kind of stuff is that? Chapter 19 would have told you that in a second. What? Look at the chapter title for chapter 19. Did you even look at 19? Come on, it's right on the back of the book. Look at the back of the book, the back cover of the textbook. Back cover. Chapter 19. Acids and base. So, what is this guy going to be? What is it? We already have acids. So what does it have to be? It is a base. Now, this guy being a base, do you have any other examples of what might be bases? There we go. What else could be a base? Any metal with hydroxide. Name a few. Huh? Metal. Metal. Do you know where the metals are on the chart? By the way, you're not the first one to have this trouble. Everybody's having this trouble, so don't feel bad, okay? Now, do you know where the metals are on the periodic chart? Okay, where are they? How do you know which is metal and which is non-metal? Huh? The metals are in the middle and all the way to the left. Everything to the left of the stair step. Okay? Those are all metals. So, any metal with hydroxide. Name a few. Okay, tungsten. Tungsten is W. Tungsten hydroxide is how you'd say that. Okay? Try to stick with the first two columns. They're easier. Give me a couple more. We have sodium hydroxide. What other do we have? What? Hydrogen hydroxide? Oh, titanium. Titanium hydroxide. Okay, fine. Stick with the first two columns, please. They're the more common ones. Anything from the first two columns except hydrogen. HOH would be water. Iron hydroxide. Can you stick with the first two columns, please? Well, open up your textbook to the inside back cover. You've got a nice one right there. Okay, what you're looking at right now is just what we were talking about in our demonstration to show what an electrolyte is. It's something that forms ions, and it's important because when you form ions, you get more particles in the water. Okay, every ionic compound gives you at least 2 particles for every molecule that you put in the water. That's a pretty good deal. It's 2 for 1. Okay, and it affects the melting and boiling points, which is what this lesson is all about. Okay, you had to have a little background first. So let's move on. We've looked at molarity and molality before, and notice moles of solute. Okay, in this way, these two things are the same, aren't they? Okay, this guy, liters of solution, is very different than kilograms of solvent. Not the same. When we're talking about molality, which is what we use to predict how much the melting point or boiling point will go up or down, that's what we're going to use, is the molality. But we're not going to use the molality of the solution. We're going to use the molality of the particles. And you'll understand that as we move on. Here's the deal. It's the real deal. So, if you look at boiling point, that's what BP stands for. Boiling point will go up when we put things in the water. And there's good reasons for that, which we're not going to talk about right now, but just be satisfied with boiling points always go up as we add either an ionic or a non-ionic compound. If it dissolves in the water, it makes the boiling point go up. I don't understand why anybody would not be taking notes right now. Okay, 100 degrees is the boiling point of water. 0 degrees, we're talking centigrade. So, freezing point is always a downward motion. So, if I have water with nothing in it, the freezing point will be at 0 degrees centigrade. However, if I move the freezing, or if I move the number of solutes up, and I put a lot more, or I put a lot of solutes, period, I put solutes in the water, the freezing point is coming from 0 down to as far as it will go with the solute that I choose to put in. So let's go next to page 472. Would you please all turn there right now in your textbook? You're going to see this chart. You're going to be using this chart in your homework. Your homework will give you the opportunity to not only do this with water, but you will always also be able to do it with. So most of the time you're going to be using water. However, some of your problems will use benzene or carbon tetrachloride or ethanol or chloroform. All of them have a different boiling point. Oh my. That's not good. Let's put that back where it belongs. All of them will have a different boiling point, but they will all, let's take just a second and make this guy not do that again. Locking. Lock that baby. Okay, now I won't do that again. So, each of these has their own boiling point. They also have a K sub B. That's called the equilibrium constant. So the equilibrium constant is what you're going to have to pull out of this table, or if you're doing it with freezing points, you're going to be pulling it out of this table. Same guy. Look, he looks very similar, doesn't he? Well, Chris, what are the units of measure for the freezing point and boiling point? The constants, what are their measures? Units of measure.
Celsius.
Degrees Celsius per molality is the way you say that.
What?
Okay. This is the boiling point constant, which is degrees centigrade per molality. So, with boiling point of water, the constant would be 0.0512 degrees centigrade per molality. Hope that makes a little bit of sense. It'll make more sense as we go into some problems. So with freezing point going up, or down, I'm sorry, freezing point going down and boiling point going up, we have to do that calculation using, anyway, this guy is the constant for our boiling point calculations, and this guy is the constant for our freezing point calculations. And with the freezing point, one more time, I haven't got these locked down yet. Anyway, for the freezing point, we're always going down. For the boiling point, we're always going up. Now, let's go to our next slide where we're actually going to do some calculations. And actually, I've cleaned this up a little bit, and I think this will make a little bit more sense to you. Okay, more particles in the water. And, okay, more particles in the water make a bigger change. So the changes are going to be given to us by the chart like we just saw. This is the same chart. And let's go back here now, and this is an actual problem. I'd like you to write this whole thing down because it will make a huge difference for you. Molality. If the molality is 1, just 1, okay. I'm going to use molality of 1 for 3 different problems. And you may have to get this online, I don't know. But we're short on time. With this guy, this is the sugar. Okay? Sugar and spice and everything nice. Everything not so nice. Anyway, in this guy, you see that sugar is going to be put into water. Sugar, the solid, that's what I just did in the demonstration, is going to be put into the water, and when it goes into the water, it will become what is called aqueous. Here. Okay, So how many particles of sugar will I have for each particle that dissolves in the water? 1. Very good. That's 1. Now, that's what you're going to do in this little guy. First of all, we have to get the numbers out of the charts. I've already taken those out so we can use those for reference. And now let's go. So here is the constant from over here. This came out of the chart, and the constant is in degrees centigrade per molality. Here it is again. This is in my calculation now. Let's just do one row at a time. Times 1 molality over 1, because 1 was the molality that I gave you in the original problem. That's the given. So 1 times this gives you 0.512 degrees centigrade, which is the delta T sub B. And you will see that in your textbook. That's the way you're calculating the change in temperature. Now it's a boiling point change. So is it going to go up or down? Boiling point changes always go up. All right, let's see how that works out in the calculation. Here we are again for the melting point, or the freezing point, I'm sorry. They're the same thing. But here's the number from the chart. 1 times that gives us a 1.86 degree change in the freezing point. Look, the freezing point changes more than the boiling point, doesn't it? A lot more. Now, just relax a minute. So now when we look at the actual calculation for boiling point, or when we take the result of the calculation for boiling point, which was this number right here, we're going to add that number to the original boiling point out of the chart. And that gives us a total of, for the new boiling point, with a 1 mole solution of water, the boiling point will be 100 degrees 0.512, 100.512 degrees centigrade. And the freezing point, now we have to add that to, or subtract that from 0, which is the freezing point of water from the chart. And so that is going to get subtracted and become a minus 1.86. And that's the calculation when we have a non-electrolyte. Now, let's go on to an electrolyte. Now, we're going to do the same problem, only we're going to use an electrolyte. So, I've got a 1 mole solution again, only this time I'm using sodium chloride. And we're still going to find the boiling point and freezing point when I have a 1 mole solution of salt in water, also known as an aqueous solution. So, right here is the chemistry behind what happens. Salt is a solid, going to get put into water, and when it does, it's going to break into particles, which is why the light lit up on the conductivity tester for the video that we made in class. And so for 1 particle of sodium chloride, I wind up with 2 particles of aqueous solution. So when I say electrolyte, that's what we're talking about. We're going to get 2 or 3 or 4 for every molecule of the solute, which we're dissolving in. Now, what does that mean for the total particles? Stop the recording just a minute, see if you can figure that out for yourself, and then start it back. Okay, I hope you figured out that is 2. So, let's continue with the calculation. Here we are. We're going to have to use the chart again. Okay, so I've got to uncover this, and I have to take all of these values and use them in my calculations. So we'll take them one at a time. All right, in our first calculation, we're starting out with the same number we had in the last calculation. 0.512 degrees centigrade. And that is over molality. Then, because in this problem we have sodium chloride, which forms two particles, and we got that uncovered. That's what we came up with here. So that multiplies the molality, whatever it is. In this case, the molality was 1. But because I get 2 for each molecule of solute, I have to make this a 2. Now, when I multiply that out, look what happens. We cancel our molalities, and we wind up with just degrees centigrade. And now we have 1.024 degrees centigrade, and that is the change in the boiling point. Now, if we go down, and we'll do the calculation now for the melting point, and you see the boiling point thing came from here. The constant for the freezing point came from here, and that's where this number came from. And this is all in the charts. Okay, so we've got this guy with the unit of measure from the constant, which is degrees centigrade per molality. Well, again, we use 2 because in this particular molecule we get 2 particles. The total particles are 2 for each one that we are actually putting into the water of the sodium chloride. So it doubles the molality. And now we can see that this number is twice what the last one was, and that's the change in our freezing point. So our freezing point has gone down, and the melting point has gone up. And that's where this calculation comes in. The new boiling point is the boiling point of pure water plus what we calculated to be the change in boiling point, which is now giving us 101.024, and that is in degrees centigrade. That's our new boiling point. The new freezing point is right here, and we start out at 0 because that's the freezing point of water, and we use this guy to do the calculation and come up with this number. And so the freezing point starts out at 0, but now instead of adding the number that we got for the change in temperature, as we did with the boiling point, we have to subtract it, because boiling points always go down as we add more stuff. And that's where we get our minus 3.72 degrees centigrade. Now, when I put these guys side by side, you can see exactly what went on from one to the next. The side-by-side view is very, very helpful. So over here, I had a 1, okay, because this guy over here is a non-electrolyte. Okay, that's glucose. This guy over here, on this one, is an electrolyte, and it gave me 2 particles for each. And as we look down in the calculations here, I haven't canceled everything out. Let's go ahead and do that. There's the molality canceling out there. And you'll notice back on the left side, molality cancels out over there as well. And molality cancels there as well. So my molalities are gone, and all I have left is my actual temperature changes. And now the temperature change here, look at the difference. That's a huge difference in our going down of the temperature, or raising of the temperature. That's boiling point. And then you look right below it, and you see that on the left side, where we had a non-electrolyte, the freezing point only went down 1.86 degrees centigrade, where on the boiling point, it went, or the freezing point, I'm sorry, on the sodium chloride side, the right side of the screen now, that guy went down minus 3.72 degrees. Okay, so there you're seeing how you're actually going to use the molality to calculate how much the freezing and boiling points will go up or down. Freezing point and boiling point, the boiling point going up and the freezing point going down. You'll calculate exactly how much that will be based on how much you put in there. So if you were a chemist and you were trying to mix up a solution that would give you a freezing point depression of 3.72 degrees, because you're going to put this out on some snow, you want to melt the snow like they do back east, they put salt out on the road. That's why they do it, because it lowers that freezing point. And let's look back at the little display that I did with the melting point, boiling point physically here. Here we go. See, if I'm way down here, my solution is not going to be melting until freezing. It's not going to freeze until I get to a little bit below the 0 degrees centigrade. So you can have ice on the road at 0 degrees centigrade, which is liquid. And so it runs off the road, doesn't cause a problem with slush and black ice and all of that nonsense that causes so many accidents. So we want the freezing point down here. We really don't want it up here because it's close to 0 degrees centigrade. So down it goes. And there's other applications for boiling points. I'm not going to go into that right now, but you can see what's happening. Freezing point change always means down, and boiling point change always means up. And I think you'll find this very, very helpful for your homework. There we go. Okay. Let's get you guys back up here to your whiteboard. Thank you to most of you who were courteous as you came in and you realized that I was making a recording. I think I'm going to trim that video. Anyway.
Your finger's not going.
All right.